so much. It's such a delight to be here. So what was I doing back in '85 here? I was a graduate student at Cornell, and my advisor went on sabbatical here for the whole year, and so I got to hang out as a graduate student. He took 6 graduate students from Cornell here, and we got to hang out and eat lots of cookies and hang out and play very, very primitive computer games in the computer room. This was all back when it was in Ellison Hall, but that was such a delight. So it's great to be back here. So let me first give you a disclaimer. I don't actually do climate simulations. Yeah, I do quantum simulations, but I share a computer with a really superb group of climate simulation people at UC Irvine. We're in the same school, one building over, and so I've been hearing about what they do. And as I've learned what they've done, I realized, well, there's really a lot of connections between what I do and what they do, and it really makes sort of an interesting story. And so that's how this talk was born. So it's a talk about chaos, quantum mechanics, and computers, and I want to start with the computers part of it. And so I have some results from some simulations up here. The one up here, again, this is not my area. This is a simulation of dark matter called the Millennium simulation, a simulation that involves simulating 10 billion particles and composed about 10 million galaxies, and it shows the whole structure of the universe in terms of dark matter. And it has these fascinating graphics that I saw at a computational physics conference, and so I decided to show it here. Over here, we know that computer simulations are now an essential ingredient for progress, both in science, many areas of science, almost all areas of science, and also in technology. Here's a little example of simulating the Navier-Stokes equations that tell you how the air flows around a vehicle. And then this last one is a simulation of quantum spins. This is my guy. I did the simulations. I designed the little graphics here. I spent 2 or 3 hours designing these arrows to make them look exactly right with the ray tracing. So I like making movies like this because quantum mechanics is so hard to understand that anything you can do to help your audience, of physicists generally, that anything you can do to help them understand what's going on is well worth it. And so in this case, it's showing an algorithm that I developed that is showing quantum mechanical wave functions, but also when the temperature is not 0, where they're more complicated. And it's sort of switching back and forth between classical physics and quantum mechanical physics. But I'm not going to get into details like that. This is about much simpler things. And so let me continue with using a computer to understand physics. So when you do physics, theoretical physics, you have to decide whether you're going to do pencil and paper or a computer. And so let's take a very early example of figuring out planetary motion. So Isaac Newton used pencil and paper to figure out, he managed to prove Kepler's first law. He derived the ellipses that the planets follow around the sun. Of course, before he did that, he had to invent the laws that he was trying to solve. This part of it, he was taking the laws and solving them. And that's mostly what we're talking about here when we know the laws already and we're trying to solve them. But of course, Newton, before that, he invented classical mechanics. He invented calculus along the way. He was one of the most, maybe the most amazing scientist ever. And so that part, of course, computers don't really do that. And so that's a separate thing. And Newton was a very interesting person. I don't know if you've ever read just the Wikipedia article on him, but here's this famous saying by him that's very noble. If I have seen further, it is only by standing on the shoulders of giants. But Newton was a very interesting, complicated person, and we think of him as standing, above it all, but he actually had a fierce rivalry with someone named Hooke. And so this, they think, may have been a slight dig at Hooke, because it turns out Hooke was a very, very short man. So So back to this problem, Newton figured out the simple problem of the planets moving around the sun, and that's an easier problem because the sun is so massive that it dominates everything, and so it simplifies the problem. But as soon as you have 3 or more objects that are not dominated by one, then this sort of analytic approach becomes almost impossible. And so at that point, you have to put problems on the computer. And so here's an example of one of the Cassini spacecraft when it went to make its tour around Saturn and all the orbits that it did. And of course, there's no way that you could write a simple equation for that. So when you get many problems, you just are forced to go on a computer. And then there's the question, well, how do you go about doing that? And there's sort of a universal procedure for putting things on the computer in physics, and that involves breaking up the problem into little bitty pieces that are so simple you can write down a simple approach that the computer can do, but you just put those pieces together, and that solves a much harder problem. So here is the standard computational approach to physics. You break it up into little pieces. So for instance, suppose we wanted to just look at a particle moving along, and here's this blue line is the path that it would take. And so the way we put it on a computer is we imagine that for a very short time it just moves in a straight line. So the straight line is simple enough to put on the computer very easily, but then you move it for a straight line and then you recalculate what its velocity should be, you recalculate the forces, and then you move it for another little straight line. And if you make these lines shorter and shorter, they approach the exact result. And so this is the sort of general approach. For simulating weather and climate, you do basically the same thing, except now you take the surface of the Earth, all the atmospheres and oceans and things, and you break them up into little cubes. And you assume that over a little cube, and I say little, but the Earth is so big that little cube might be a mile cubed. And you break it into a little piece, and you assume that over that cube, everything is constant. The temperature's the same over the cube, the wind velocity, the pressure. And so you can write down simple rules for how that behaves interacting with its neighboring cubes. And then this all becomes exact when you make the cubes smaller and smaller. And so you need a bigger and bigger computer to make them smaller and smaller. And as the supercomputers have gotten more and more powerful, we can do this better and better. So this idea of breaking things up into little pieces to solve them, the earliest example I could find was Archimedes, who wanted to estimate pi, and so he started drawing polygons around a circle and then inside the circle, and he could calculate the area of those polygons, and then he did it for a 96gon, and he got this rather nice bound. They're both those numbers are around 3.14. So it was a nice calculation way back. Okay, but so now let's progress from hard calculations to what you should really think of as impossible calculations. So an example of a hard one is people have actually simulated the motion of the planets around the sun for around 1 billion years. And that's a very hard calculation, but it's doable. But what Poincaré found out was that if you just have 3 planets, but you make them all the same mass so that one isn't dominating the others, then you get something very different. You get chaos. And chaos can show itself with these planets, that you might have all 3 planets sort of moving around each other for a while, and it looks like they'll just stay close by, revolving around each other, and then all of a sudden one of them shoots off, and it has enough energy to keep going off to infinity, and all of a sudden you have 2 sitting there, and one's gone off. And that's chaos. And when you look at the different sorts of chaotic systems, another one is weather, these weird things that they do are different, but they have a common feature. And the common feature is that if you look at what these things do, and then you change something at the very beginning, just a tiny little bit, you could think of this as a tiny little error that you made in what you thought they were going to do, this difference between them, this error, grows more and more rapidly. It grows exponentially, extremely quickly with time. And so if you go a fair amount of time, you just can't do it anymore. You can't do it accurately. It requires exponentially more effort.
So
Yeah.
I'm going to ask a question partly to teach everybody you can ask questions. Poincaré was able to figure out that three planets orbiting would lead to chaotic, but he didn't have a situation.
Right.
So how did he do it?
I think he worked very hard. I mean, there was. Yeah, I don't know all the details about how he did this. I was thinking about this before the talk. People back then, they worked very hard carrying things out by hand as far as they could. And he probably also had some clever mathematics to help him out along the way, but I don't really know the details. So you can understand chaos in a simpler system than these planets, and so you can understand it in the example of pool or billiards. But the first example was due to Sinai, who did something called Sinai billiards, which doesn't look much like billiards, but it has one circle that's a hard surface that a particle would bounce off without any energy loss, and then it's all inside a square, and you just have a particle bouncing around inside here. And this turns out you can it's a fairly simple problem, and you can analyze it, and you find that it exhibits chaos. Okay, but we can also see chaos at a real pool table, and so I'm going to show you a little home movie that I made to illustrate chaos. So do we have this? Hi, I'm outside the student center, and you see Irvine, home of the ampere, and we're going to do a demonstration of chaos using a pool table. What we have is a pool table with all pool balls lined up, and the material lined up as actively as we can. We use two other pool cubes to line them up. And then at the end, we have a wine glass with 60 moles in it. And the idea is, we might use this to try to hustle some money if you like. But what we really try to do is just shoot the cue ball in the first one ball, and then do that one with the blue ball, then the green ball, blue ball, blue ball, and then the eight ball is the wine glass. Then somebody gets the money. And of course, when we do this, we look at the pool sticks there. And it turns out that this is remarkably difficult to get small balls to go to the straight lines and not veer off course and hit the wine glass. Okay, now we're back to the best shot in slow motion.
You took a lesson in between.
So thanks to a couple of my kids helping with making that movie. Let's raise this up. And so, does anybody remember back from high school trigonometry? Did you ever hear of something called the law of sines? I heard. Anybody actually remember what it is? Well, if anybody remembers, you can help me derive chaos for this problem, because that's all it takes. A little bit of high school trig, that's it. Okay, so let's do that. Okay, so we're going to take one of the balls here, and here's the other one, and we draw the ball here. It goes along in this line here, and there's a collision. Oops. Okay, that's supposed to be through the center of the ball. And the horizontal line is through here, and then let me draw this line up here. Okay, so I always make a little error in the beginning. I try to shoot it in exactly in a straight line, but I make a little error, and so I have a little angle here, theta 1. Okay, and then when it collides, you have to know a little bit of physics. A little bit of physics you need to know about this problem is that pool balls are hard. That's it. So when they collide at one point, and then the other ball goes immediately away on this line between the two centers, because there's an instant of force, and you know exactly which way that force goes. And so there's an angle theta 2 here. And so what we would like to know is if you have this little error theta 1, what is the error theta 2? And all you really need to know for this is the law of sines. So first of all, if this is theta 1, what is that angle? Theta 1 also. Theta 2.
Theta 2.
Okay, so that's theta 2. Okay, distances. I need to know a couple of distances. So now I need to know the distances when the angles are very small. So let me redraw this with very small angles, because we're not really interested so much when the angles are big, because once the angles are big, you know it's going to miss right away. So let me define the distances between these two billiard balls as L. So L is the distance between the close edges of the ball, and then I've got a diameter of the ball, D. Okay, so you can see that this leg of the triangle is 2 radii, so that's D here. Okay, so these points are this point, and that point. Okay, over here I have theta 1. Over here I have theta 2. And then what are the legs of the triangle? Well, this is L between the close edges. So if I want to go to the centers, it's L plus D. So that's L plus D. And then if the angles are very small, these are almost perfectly lined up. So this one is just L. Okay, so there's my triangle. Okay, did anybody call up out of their backup hard drive what the law of sines is? I want to find a formula that has theta 2.
It's 2R.
Yeah, D is 2R. Great. Okay, so the law of sines says that sine theta 2 over the opposite side is L is equal to sine theta 1, this guy, over D. And you can do it for the third side and angle, but we don't need that. Okay, that's all the law of sines is. Okay, need one more little piece, which is that for small theta, sine theta is very close to theta itself. Okay, so with that, and we're only looking at this when the angles are very small, we get theta 2 over L is equal to theta 1 over D. Solve it for theta 2. and I get L over D theta 1. Okay, so it maybe in that example, L over D was maybe around 10. It varied a bit. But if this is around 10, your starting error, if that was 1 degree, all of a sudden it's 10 degrees. And then 10 degrees goes to 100 degrees, and then it doesn't work at all. Okay, but more important, even if a really good pool player can, maybe my errors were 1 degree or 2 degrees. If they can do 0.1 degree, it only gives them an extra ball. Right? You know, so let's put it together. Let's look at theta n. So you keep doing this. Every time you multiply it by this factor of L over D, and you get theta n is equal to theta 1 times this factor L over D to the n minus 1. Okay, so no matter how good the pool player is, they're not good. Your money is safe. If anybody uses this to hustle some money, the KITP would like a cut. Okay, so this is chaos. This is all it is. And you actually see in the same system that it can be non-chaotic. So suppose the balls are closer than 1 diameter together, then L over D can be less than 1. Okay, so if they were 1 radius apart from touching, then this would be a factor of 1/2. And every time it hit another ball, it would get twice as accurate. And so you would have something that it doesn't go off crazy, it would hit every time. Okay, maybe that'll help with the hustling a little bit. But it does make clear that this case where I did pretty well, it had the balls a little bit closer together. Okay, so that is chaos. Let's have the screen down again. Okay, how does this relate to the weather? Well, so some of the very first computer simulations of the weather by a man named Lorentz showed chaos. And so chaos in this sort of system is whenever you have the sort of, instead of a smooth flow, you have this sort of irregular flow with vortices and things. That's a sign of chaos. And so the first simulations show that weather had chaos. So all of a sudden the idea of predicting the weather for a really long time is basically impossible. So this, you hear about it, the butterfly effect is basically talking about this. They even have a movie about it. But it's from a talk that Lorentz gave to the AAAS in 1972 titled "Predictability, Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas?" And so the idea is that even a thing as small as a butterfly flapping far away, if it keeps growing exponentially, eventually it will be big enough to change things completely. So the basic thing that you need to know about this is what is the sort of rate of growth. This factor of 10 here, L over D, that's the key thing that tells you how fast it grows. And so there's a time scale for weather prediction that's about a week. So what that means is that you're fine for predicting weather with a big computer for about a week, and 2 weeks, they're doing okay now. Not too accurate, but if you say 2 months, it's basically hopeless, and it essentially always will be.
Sir?
Yeah?
If you decrease the size of the cube, would that change the time?
No. So this is a property of the phenomenon itself. If you actually had 2 different worlds and you could throw in the butterfly into one and not in the other, it would change, the worlds would go differently. So in the computer, we're trying to reproduce what the world would do as accurately as possible. So if you do a bad calculation, it might not show the effect of the butterfly. But the better your calculation, the more it mimics the real world, and then this effect is a real effect, and there's no getting around it.
You're talking about time scale, but my question was about distance scale.
Right.
So
when you make the distance scale smaller, what you're doing is you're making it more accurate. But if you have a little bit of uncertainty at the beginning, like you don't know exactly to a millionth of a degree what the temperature is in Santa Barbara to start with your computer, well, that will just grow over time. So all the uncertainties those errors just get bigger and bigger. We can follow the equations more accurately, but it doesn't really help. Okay, so then how do we predict climate change when we can't even predict the weather for a month? That's the essential problem. Okay, let me now switch to quantum mechanics, where it turns out we have similar problems. Okay, but first let me talk about what is quantum mechanics. And of course, what we've been talking about so far is classical mechanics, the laws that Newton figured out for the most part, and that's an extremely good approximation for most of the world. But for very tiny objects, atoms, electrons, photons, etc., quantum mechanics comes in. Classical mechanics isn't right. And so we have to face this other world. And one of the key questions of quantum mechanics is if you think about particles, are they really particles like we think about them, or are they waves? But often quantum mechanics has effects on the macro scale. So here's a laser. A laser is basically a quantum effect with light. And this levitating little cube is a cube of a high temperature superconductor. Much of my career I've spent doing computer simulations of the quantum mechanics of high temperature superconductors. So this one is at liquid nitrogen temperatures, and it's above a magnet, and it's floating above the magnet because of its superconducting Meissner effect. Okay, so those are two examples of quantum effects. So let's first understand waves to try to understand the problem with quantum mechanics. So first of all, we can picture water waves very nicely. So this is all just pure water waves. So if you drop a pebble in a pond, you get these circular water waves coming out. But physicists like to do this sort of experiment where you have, it's like an ocean wave hitting, but then you have a wall with a little hole in it. We call this a slit. And then if you do this, the waves come out, they're stopped by the wall, but they come out of the slit, and they make these circular waves coming out from the slit. And you get something interesting that is the unique signature of wave phenomena when you put two slits. Because if you have two slits, and so the water just has a certain height, well, you get circles coming out of each slit. And then when those circles come together, sometimes you have a high wave coming in with a low wave from the two slits. And the rule is that you're just supposed to add those water heights together. And so if you add a high wave and a low, it can cancel out. And that's what we have along these lines here, these nodal lines. And so that makes a pattern of interference, and it's something that's unique to waves. So we can imagine measuring that by just setting up so here's a source for our waves, and then we have the wall and the two slits in it. And then they make these patterns, and then along here we have something measuring how high the waves get right there. And then we make a plot of how high those waves are, and you see this funny interference pattern. And so that's our experimental signature of waves. Okay, but if we do the same sort of experiment with bullets, they don't have interference patterns at all. And so here's a machine gun, we fire it, and maybe the bullets bounce off the wall a little bit, they get smeared out, but the one thing that it doesn't do, just because you have two slits, is have some sort of interference between them. And so if you add up where all the bullets hit and then make a plot of it, it's just going to be the sum of the plots from each of the single slits. No interference. So we have this good experiment to tell whether things are particles or waves. Okay, and so now we take a quantum particle and we say, what does it do? And this is actual experimental data from quite a ways back. One of the first experiments that did this, but what do electrons do? And the answer is they show interference patterns. So first of all, they show up as individual electrons hitting the screen. But then when you do a bunch of them and you see what the pattern is of where they hit, and if you could average, you could put them all together and add it up and make a plot, you would see these interference patterns, these regions where there just aren't many particles. So it looks like electrons are somehow waves, which when they hit the screen are particles. And that sounds crazy. And that is quantum mechanics. It sounds crazy. And the first thing you might think of, whenever there's an experiment with something mysterious, physicists try to look for what's wrong with that experiment. There's a loophole. You're not right. This can't be so weird. And so the first thing you might think of is, well, two electrons could bump into each other, and they could make this pattern, and they would interfere with each other. But the amazing thing about these patterns is that the patterns happen exactly like this, even if you send the electrons in one at a time. So that's one of the things that makes quantum mechanics so hard to understand.
A with 2 electrons and B with 1.
This was just a different separation of the slits. So the interference pattern changes when you move the slits, and you can see how the pattern changes with that and get even more evidence in favor of waves.
Excuse me.
Yeah.
Was it this experiment or similar one where the observer makes the difference?
I'll get to that in just a second. Yeah. Okay. So why do electrons interfere? Well, in some sense, we don't know, but we have mathematics that describes it. So what a physicist does is he says, well, we describe the particle by something called a wave function. And this wave function definitely acts like a wave, except when you actually hit the screen, and then it acts like a particle. And so we know how to describe that. And the wave function really goes through both of these, and then you end up with this pattern. So then you could ask, well, which slit did the electron go through when it makes this pattern? And so this is the sort of question that has puzzled physicists ever since the beginning of quantum mechanics. It's one of the things that makes it so mysterious. So suppose you try to be clever and you try to look to see which slit the electron went through. Well, to look at it, you have to shine light. Light is sort of made of particles itself, photons. So you shine some photons on it. If you shine enough photons on it with enough energy to actually see which slit the electron goes through, you bump that electron and you destroy the pattern. So Mother Nature will not let us see which slit the electron went through unless we destroy the pattern. And very strange. So if you ask which slit did the electron go through, one way to answer it is the wave function goes through both slits, and it just puts the question off. Is the particle the same as the wave function? Is the wave function real? And those are questions that, if you ask us what is real, that's a question that we really don't know how to answer. They were all a big matrix-like computer simulation. But this is so it gets into philosophy. But these are difficult questions. But this is what led Feynman to say no one understands quantum mechanics. Has anybody read these wonderful books by Feynman where he tells his stories? Surely you're joking, Mr. Feynman. So I actually got to hear Feynman tell these stories from his living room. So this was when I was an undergraduate at UC San Diego. And so back to when I was a freshman, I had this friend in my dorm named Toby, and he was a physics major too. And I knew that Toby's dad was a professor at Caltech. And so about halfway through the year, all of a sudden one of his other friends said, "Hey, did you know that Toby's dad won a Nobel Prize?" And we were like, Toby, your dad won a Nobel Prize. Why didn't you tell us? And he said, well, what am I supposed to say? My dad won a Nobel Prize. What did your dad do? So fast forward, we're senior physics majors. And we're looking at graduate schools, and we both decided to go up to UCLA. They had a big, big event where they brought in lots of potential students. And then Toby said, well, why don't we stay at my house afterwards? And he was up in Pasadena. His dad had passed away by then. His dad was the famous biophysicist Max Delbruck. So it was Toby Delbruck. And so we went to Toby's house afterwards, and we're sitting at the dinner table with his mom, and his mom said, and I knew by that point that the Delbrucks were good friends with the Feynmans. So I'm sitting at this dinner table, and Mrs. Delbrook says, "Oh, I was thinking of calling up the Feynmans and getting together next weekend." And Toby said, "Oh, why don't we do that tomorrow so Steve can come too?" And I practically fell out of my chair. And so this happened. So Feynman was a master storyteller, and we went over to his house, and we got there, and Feynman said, "Well, what do you want to talk about?" And Toby said, "Tell us some stories." And so we sat in his living room, and he told us stories. And it's a lot of the same stories that you find in these wonderful, entertaining books. Except I don't know, we may have gotten a few more, because what Toby actually said was, "Can you tell us stories about Las Vegas?" And so there may have been some extra ones there. So that was quite a thrill for a budding young physicist who was still an undergraduate. Okay, so and I must say that this description that I've been giving to you is Feynman's way of describing quantum mechanics. It's a very nice way. But now let me go to simulating quantum mechanics on a computer. So how do you do that? Well, you have to keep in mind certain things when you try to put quantum mechanics on a computer. First of all, there are some things that absolutely cannot be predicted, like which slit the particle is going to go. You can only say a probability. If you look at it, you'll find out, well, there's a 50% chance of it, say, going through one slit or the other, but you can't say exactly which answer is going to come out each time. It's just a probability. So the things that you can get from your simulation are these probabilities, or you can average things and find statistical averages. And then the other rule for quantum mechanics is that when you're not looking, sort of everything that could happen does happen. It goes through both slits when you're not looking. And every possibility combines to give the final answer. So you can see that this gets really hard. This is an artificial problem. This is not something that people normally do because it's not very interesting. But let's just imagine that we put a whole bunch of two slit things lined up one after the other. And then we had to say, well, which path did the particle go through? And you have to take into account all of them and add them all together. Well, the number of possibilities, there's 2 for the first one. For every one of those, there's 2 for the next, 2 for the next. It's 2 to the n possible paths. And so as soon as you start thinking about putting quantum mechanics with lots of things, and more generally with lots of particles, those are the interesting problems, it's immediately exponential like this. And so just like simulating chaos, things get bad exponentially. You need an exponentially fast computer. You need an exponentially fast computer to simulate quantum mechanics to do this. So that's a key way that these two areas are the same. Okay, so let's look at these similarities. So it turns out that so these similarities are more than just this exponential problem. It turns out in both cases there are some questions that we would like to answer that we just have to give up on answering. So you have to give up on predicting precisely which slit, and you have to give up on predicting whether it will rain on a specific date, like Christmas, far in the future. So the averages that we can, the questions that we can answer are usually about some sort of averages that lump things together. So you can get probabilities and averages. So a climate example would be, what will the worldwide average July temperature be next year? So if it's over all of July, you might be able to get a pretty good answer. The other thing is that the way you attack this problem is you use essentially dice. So Einstein said God does not throw dice, and what he meant by that is that this randomness, that you don't know which slit the answer will be, he didn't like that appearing in quantum mechanics. It was a very strange thing, and he didn't like it, and so he kept trying to find ways around it. But in terms of doing quantum mechanics on a computer, this is actually very useful, because one of the best ways of dealing with chaos in quantum mechanics to get an answer is actually to roll the dice ourselves. So the quantum mechanics is doing its roll of the dice. Let's roll our own dice. Okay. So let's talk about simulating climate. Now, since the election is coming up, let's talk about the election. This is just like polling, really. This is just like doing a poll for the election. If you just call up your friends and say who's going to win the election, you're not going to get a very reliable answer. You have to pick people across the country and do it randomly. And if you do it randomly, if you really had to get the exact answer, you'd have to ask everybody in the country, and that'd be too hard. Except it's possible because the census does get everybody in the country, just about. But to predict the election with just talking to a limited number of people, you have to choose them at random. And then the magic of taking a poll is that if you do choose these people completely at random, it gives you a pretty good answer, regardless of what the whole population of the country is. So if you ask 100 people, you'll probably get your answer good to about 10%. And the rule is you take the square root of 100, and that's 10, flip it over, and that's 10%. And that's the way polls work. And it doesn't matter whether you're taking a population of a city or the whole world. So this idea of statistical sampling is used in many areas, including climate change. So how does this work in climate change? Okay, so what do you do? So first of all, we have to restrict the answers that we want. We want to look at averages over large areas and long times so that the weather effects average out. And then we roll the dice. So what does that mean when you do these climate simulations? Well, you don't know exactly what the weather was at the start of your simulation. Maybe you start your simulation 500 years ago, and then you're going to make it go forward in time and look how the weather changes over time and do it for 1,000 years. And you don't know exactly what the weather was, or exactly what the temperature was, the wind, all those things when you start. So what you do is you guess, but you do it with a random distribution. So you say, well, we know it was within this range of temperatures. Let's assume a bell-shaped curve and pick from that curve and use that as a starting point. And you do that with all of the unknowns. You make all of the unknowns chosen randomly. And so this is very interesting because if you did know everything exactly, you still wouldn't be able to simulate it anyway because the chaos would come in and make it not work. But if you choose things randomly, then that turns out to work quite well. And so here is an example of this sort of climate change. I'm not in this field, so I only found a slightly older example. But they do simulations simultaneously. Nowadays they do, hundreds of climate simulations simultaneously. It's called an ensemble of simulations. And so here's an example of the temperature from a bunch of these simulations. And you can see they all vary. They're all randomly. They would all have different weather on Christmas, but they all follow a general path. And so you can draw the average for that. And then you can put error bars around it. And again, it's just sort of like doing the polling. And you can get a real answer. And so this is what they do in it. And it's really impressive to see in some of the talks I've seen when they really have many of these. It's very impressive to see how they duplicate each other and you see interesting effects. So here's another example for the precipitation, and you see these patterns, and here you're seeing a real pattern that you try to find out if it was real. But anyway, this is sort of the essence of this way of simulating things. So how about quantum mechanics? Okay, so we have this problem of so many different paths. How can we deal with that? Well, we're going to choose the paths at random. And so here I'm talking a little bit about this relationship to polling. But in the quantum mechanics example, we're going to choose the paths at random. And this is where this method originally, it was originally developed in an area of physics at Los Alamos. And back at that time, they were rolling the dice, and the big city for gambling was Monte Carlo. And so it got the name Monte Carlo. Nowadays, more gambling is done at, say, Las Vegas, and so if you named it today, you might say it was Quantum Las Vegas. But so we pick them at random, and then we add them up and we average them. And this works no matter how many paths we have. And the numbers in physics get really huge. Like you might have 10 to the 1,000 paths. But you can add them all up and get statistics, and it works quite nicely. Okay, so how important is this? So one way to find out how important something is you can ask Google. Google knows many things. And so Google has Google Scholar, that's specialized scientific search engine. And so you can find out something about what's going on by searching for phrases. And so if you search for quantum Monte Carlo with quotes around it for Google Scholar, you get about 24,000 hits. So this is a pretty big scientific endeavor. And so this sort of technique is used to understand high temperature superconductivity, quark structure of protons and neutrons. It's called lattice gauge theory. Things like spin liquids, which is something I work on, the chemistry of molecules. What's interesting is that this technique has spread to just about every area of science. And so if you do a search on just Monte Carlo to Google Scholar, you get about 2 million hits. And this is even used in experimental areas of physics, like if you want to find out how the LHC, the Large Hadron Collider that's just found the Higgs, how that's working in detail and calibrated, you do it with Monte Carlo. This is an example, a real-world example of doing this quantum Monte Carlo. And so this shows some spins. And so this is an example of how instead of the two slits, one after the other, giving you to this 2 to the n, these quantum spins can actually just be up or down. And so if you look at all the possible patterns of spins, the first one can be up or down. For each of those, the second one can be up or down, etc. And so you get 2 to the n again. So when we try to understand these spin systems, we have a problem that's exponentially large, 2 to the n. But this is an important problem because this is the description of what's called the parent compound of a high-temperature superconductor. So the high-temperature superconductors are these special materials. I showed the picture at the beginning that have superconductivity up to about 100 degrees Kelvin. But the parent compound is what you start with, and then you add, you change the recipe away from that to introduce mobile particles. It's called doping, and you get a superconductor. So this is not a superconductor. It's what you start with, and then you add something to it, and you get the superconductor. So this is very important, and this was one of the key successes of quantum Monte Carlo in my field. Okay, so we're almost done here. Does this quantum Monte Carlo always work? And unfortunately, the answer is no, because quantum mechanics is extra hard. When you add up the wave heights of the water, you just add them up. But when you add up things in quantum mechanics, sometimes they have minus signs. And what that means is that sometimes you try to think about, like you're thinking about calling people at random, and you want the same probability to call each person. But in quantum mechanics, sometimes those probabilities, or what you would like to have as probabilities, are negative. So you say, well, a certain particle, I need to check that one with a negative 50% probability. And that just doesn't work. That's what quantum mechanics gives you. And so we can't really use this quantum Monte Carlo method very well in those sorts of cases. So it turns out that there's a lot of the interesting problems in quantum mechanics that people like me are interested in are stuck with this very useful technique because of these minus signs. It's actually called the minus sign problem. So what do you do? Well, that is the subject of that's the subject of another talk. That's what people in our current workshop are like me are focusing on. What do you do when you can't use this nice technique? And we are making progress in an area called quantum spin liquids. And this is a simulation that I did on quantum spin liquids. It's showing something that's there and then it vanishes. What does that mean? Well, this is showing a pattern that's showing the deviation away from the average for all of these. There's spins here, and the spins sort of make bonds. And it's showing that when you simulate these with the full quantum mechanics, they all go back to the average. And this is a sign of a quantum spin liquid. And so this is also, we managed to get on the cover of Science magazine just last June with the simulations that are shown here. And that's also my artwork.
How did the term liquid come? What is that
Yeah, so if you
concept?
Yeah, so if you think about what a gas is, the molecules are all random. If you think about a solid, it's all locked up. If you think about a liquid, they're very ordered if you look microscopically close together, but you look farther away and they're all moving around. Okay, so these spins do the same thing. If you look closely, I was showing you pictures of spins that were up and down. If you look closely, the spins are all in these little bonds. So they have structure close up. But when you look at distances far away, and the amazing thing is that it happens even at absolute zero. Right? You heat something up and it always melts. How can something melt at zero temperature? Quantum fluctuations. So a spin liquid is something that the quantum fluctuations are so strong that they melt everything even at zero temperature, yet there's still sort of microscopic structure that makes them very interesting.
Feynman was right.
Well, he was right about many things. Yeah, okay.
Have you found any application of this toward quantum computing?
Yeah, so yes. So, of course, you talk about applications, and the first question you might ask is, well, will quantum computing itself have applications? We hope so, and then you can say, okay, our application is, well, this might help you build a quantum computer. And so it turns out that this sort of combination of microscopic structure but long-distance fluctuations helps it have exotic particles as excitations that can actually be used to hold qubits. And so this is a central interest of Station Q just over in the next building. Their whole goal is to understand how to build a quantum computer. And so one of their key areas is to look at things like spin liquids, because they have the potential to hold qubits in a sort of robust way that doesn't have the problem of decoherence. Okay, but that's another talk. Okay, so in summary, you look at simulating chaos and quantum mechanics. For both of them, there are some questions we would like to answer, but they can't be answered. The questions that we can ask and get an answer are often averages and probabilities. Both of them have this exponential difficulty, but you can get around them by rolling the dice yourself and using randomness as an ally in the simulation, and that produces something called Monte Carlo or quantum Monte Carlo. And then the forefront of research in this is what to do when this wonderful technique doesn't work because of the further weirdness of quantum mechanics. Okay, thanks to the KITP, the National Science Foundation, for funding my research for a long time. And thank you for your attention. A couple of books that are very nice: 6 Easy Pieces by Richard Feynman and Chaos, Making of a New Science by James Gleick. Thanks.
Okay, let's take some questions. Yes?
It's a little off topic, but I'm really confounded by quantum entanglement. Do you have any insight into how things change instantly regardless of distance for the spin?
Well, I've certainly thought about that a lot. Let's see, the question is, can I, let's see. So when you talk about quantum entanglement and things change instantly, one way of thinking about that is that both possibilities were sort of already there. And what you're doing when you measure one particle and it's entangled with another one far away is you're sort of entangling yourself locally with one state of the particle. And then the particles themselves are correlated with each other. So you sort of tie yourself up with one state of the particle, and that automatically just leaves your world having this other state far away. So when you think about it this way, you're sort of driven a little bit towards this many worlds idea, that, you think of the particles as being up and down or down and up. Sometimes it's easier to think about that if you say, well, there's sort of two worlds that are, one's that's up and one's down. And when you sort of look at one, you're just sort of splitting yourself off with one of them compared to the other. But it's a very difficult thing to get your head around. And there are different
The more I read
ways of
about it,
looking.
the less I think anybody understands.
Yeah. It's that's like what Feynman said. But we know how to do the math for, and so in some sense our brains are not hardwired so well to think about these things, but we can do the math to figure out what's going to happen, and these quantum spin liquids are all about entanglement. That's really what makes them different, is that things are entangled with each other far across this system. And it's a very interesting thing. The entanglement is even the key ingredient to the quantum simulations that we're doing to get around the sign problem. So it's an extremely important
theory,
topic.
if you could control it like zeros and ones with spin, you could have computers interconnected regardless of distance.
Well, there are it's known that you can't really use this to communicate in a normal fashion. So it's sort of provable that it doesn't work as a better way of communicating faster than light.
I thought I read
When you actually try to use it as a communication tool, all that sort of gives you is that when you look, you have somebody on a different planet and you try to send messages and you have two spins and you each measure them and you do things like that. And you find out you don't really have any information. You just got some up or downs here. There's no way of figuring it out. When you come back together with your friend, you'll find that those answers were correlated. But it's just impossible to use it as a communications. Another strange thing.
Question back there.
I want to ask a very applied question. What are the applications if you are successful in quantum Monte Carlo?
Well, so one of the things we're trying to one of the things that I've worked with for a long time since I was here at UCSB as a postdoc was to try to understand the high temperature superconductors. So those are also a very strongly correlated system that we use quantum Monte Carlo for, that we use the other techniques for. And so the main goal in doing that, the first thing is just to understand something that you don't understand. You can't really make progress towards any application or anything if you just don't understand what's going on. So that's always the first thing. We don't understand this. It doesn't fit with our existing theories and framework. Let's try to understand it. Okay, and so then once you understand it, well, people like me will probably move on. But usually what happens is people understand and they say, oh, I know a clever thing that I can do with that. And then that can lead to sort of totally unpredictable applications. So there's things like high temperature superconductors, the spin liquids. Again, it's a sort of remote application because there are no quantum computers yet. We don't know if they're useful, but it's intellectually really fascinating. Quantum mechanics is, everybody, physicists think that their area of physics is the most fascinating. I think quantum mechanics is the deep mystery of the universe, and so it's really interesting to try to figure out what's going on.
It seems to me you've become a much more tolerant man having studied this field. Is that true?
Well,
that's a rhetorical.
Yeah. I am tolerant of many fields of all that we do at a university. I like lots of things that people do. So I guess I am pretty tolerant. There are a few that I don't like so much, but I won't talk about them.
It would seem the field would have made you more tolerant.
Yeah. Humble.
More humble.
I had a question. You mentioned the sign problem a number of times, and you said that methods don't work on it. Your typical methods don't work on it. If you had a computer that had unlimited resources, exponentially, increasing resources, would you still have a sign problem? I mean, would it still be a problem?
So what the sign problem does is it turns a problem that is tractable, because you can do the sampling. And so the sampling sort of gets rid of the exponential problem. If you have the sign problem, it's back to exponential. It's no worse. It's just your trick didn't work, and you're back to the drawing board.
Okay. Other questions? Some questions here? Yes.
Some question? And just when everybody is on their way home, we'll need your badges back. Put your glasses outside. So.
Okay. All right. Well, no other questions. Let's thank Steve. Come up afterward.
Yeah. Okay.